I will
So we
indeed.
won't have that
I
problem.
don't think we need to worry about the hiccups in there and all of that. We'll go back to the original material.
Sounds like a good plan. Carl, did you want to say something? All right, Cole. I'm going to have to mute you because I can. So if any of you were confused by the various machinations towards the beginning, you can watch this whole video intact direct from Bill on YouTube at some later time. So any questions or comments?
Yeah, I'm confused. It looked to me as if he was taking like cell 1-1 of the first array and then applying the operator or whatever that was to it against cell 1-1 of the second array, and you can't do what's called matrix multiplication in that order. So I mean, addition, yeah, subtraction, yeah, but matrix multiplication is done in a specific order, and that ain't it. So I'm a little bit confused by that. Did I miss something there?
Was he missing the transposition? And I missed it. I'm not sure.
Well, if it was there, I didn't see it. I was hoping somebody would say, "Oh no, James, you idiot! It's right there. He did the transposition at this point." And I was, the whole time he was on that slide, I was like looking like, where is he doing it? And the thing is, you can't do a transposition if you're doing matrix addition. And I didn't see anything that said, you know, like if the operation is multiplication or division, do the transposition, and if it's not, then don't. So again, I'm not sure. I think that this was not. It's probably just a semantic issue. You know, people say, you know, you can do multiplication of all the elements of two matrices, or you can do quote matrix multiplication, and those are two different things. So it's probably just a semantic misunderstanding.
That difference between an inner product versus an element by element multiply. Yeah, that is a little.
One issue that is being modeled on K, and I'm gonna have a link to the K reference manual, because if you're interested in doing matrix sorts of things, the concepts in K have evolved over decades from APL. But one of the factors is because of the lists of list structures, it is like a matrix multiplication, but without the transpose. So, I mean, that's a major sort of difference in the structure of things, and that's been something dealt with. But in any case, definitely these languages that have evolved and worked with arrays of now into the gigabytes and terabytes are very, very sophisticated concepts. That's my rant.
Yeah, I guess I'm just saying that isn't what you call matrix multiplication in.
I'd
like
agree.
math.
I'd agree. It's the fundamental action of a vector. It's essentially going to go and multiply each column as opposed to each row. So if you really want to go and implement traditional matrix multiplication, you got to throw a transpose, a flip on the left argument.
So maybe that's just like a separate pre-operation that he would be doing, and then he would apply this with the multiplication.
Yeah, or you can just make a word that includes the flip. But
right. Yeah, but then you lose this ability of doing multiple different operations with the same code, which I think was kind of the point of his.
Actually, I mean, one of the things about COSI is it uses the incredibly powerful notion of the quote that the fourth has. So you've got the address of whatever function you want to apply this structure of operations to. So
yes, but this is the fourth interest group, not the COSI interest group. So I'm not sure how that applies.
It's matrix. It's just operations on arrays. You know.
Right.
Yeah.
Well, now you've got me curious enough to go back and confirm. Yeah, maybe he's muddling doing a proper inner product versus. Yeah, I confess my attention wandered as
Well,
I
I
was
just want to be
skimming through
very
that
clear.
WASM forth that you sent into the chat as you were his video.
Okay, see, now I have to apologize twice. First, I have to apologize for distracting you, and then secondly, I have to make sure that I'm being clear here that I'm absolutely certain that he knows what an actual matrix multiply is, and my assumption is that that's handled somehow, and I just missed it.
There may be some sleight of hand there, but yeah, it's a good question. We'll have to.
Why don't we talk about this next month, or if any of you want to conduct an email discussion, send your email addresses to me if you have Bill's already. You're welcome to email directly to Bill with this question. But I think trying to figure out what Bill meant in absentia is a fool's errand, since Bill is very much alive and quite communicative, if I may say that.
Yeah, it just wasn't mentioned in the video. So you guys were right in the fact that they didn't show what was going on there. So I guess we'd have to wait and ask Bill.
Let's ask Bill. All right. Does anybody have anything that they would like to talk about at this time?
It was mentioned in the chat that the Vintage Computer Festival is ongoing, expected in August. I guess it's 8 and 9. Is that right? No, Dave is shaking his head.
7 and 8.
7 and 8. Excuse me. The weekend. Yeah. And then I expect to have an exhibit there. Show some of my 4004 stuff, and should be a lot of fun. We're all anxious for it. We've had people from different countries show up. We've had people from Germany, people from England show up at these things, and people from across the United States bringing exhibits that are worthwhile. A lot of fun.
Yeah, so I'm taking a close look at the Parallax Propeller board. It has 8 cores of like 100. And also, I'm really curious about this P32, but I don't know if Dr. Ting wants to talk about that at all.
Ting, is the EP32 your processor, or is it a commercially manufactured processor that you've had eForth on?
Dr. Ting, you're muted.
I'm not hearing anything.
No, Ting is muted.
Dr. Ting, you are still muted. We didn't hear a word you said there.
Okay, EP32, we tried to manufacture it about 20 years ago in Taiwan. We have some test silicon which work correctly, but we have never been able to produce in any significant amount.
But you also have the files for FPGAs.
Yeah, it's been after I came back to US, I did it in FPGA, and it worked quite well. But it was never made out into silicon.
Which platform is it available for?
Yeah, which FPGA do you recommend I use it on?
Yeah, I think it is in the OFFET library. I think it is on the FIG website now. The VHDL file and also the test code.
Yeah, I'm really interested in the use of Forth on FPGAs. And we've had a lot of discussion about this today in the chat and back and forth as well, that I guess there's like 2 or maybe 3 different basic applications of Forth. And one of them is you're implementing it on somebody else's platform. As Dr. Ting has pointed out, you don't get to control the platform, right? You know, it is what it is, and then you have to deal with the language inefficiencies or whatever is less than ideal, and you have to implement over that, like, you know, no goto in WebAssembly or whatever. And then the other place, you know, so in that case, you have a huge potential audience, right? You can deploy it as a program or as an IDE. You can make it available in every web browser. You know, it can be everywhere. But you're running on some other platform. And then the other place is when you're implementing, you know, bare metal. And implementing bare metal on, you know, like x86 or ARM or whatever individually just seems like a losing game to me. But, you know, maybe it's not. I don't know. That's just my opinion. But implementing bare metal on interesting FPGA cores, that's really important critical work, and work that no language is better suited for than Forth. I mean, that's the place to be, where you can get something running instantly and still be able to build it into something you know, huge with efficiency. So, you know,
a lot of the FPGAs are very closed platforms. Like, yes, you can take your Forth and use the standard tool chain for whatever device and then run it inside the FPGA. But if you want the Forth to be dynamic and able to edit itself and change what else is on the FPGA sitting next to it, then you're also similarly sort of locked out, and now you have to go back to this big tool chain that has all this complexity. And so I mean, there's a handful, I guess, of semi-open source FPGAs, but those.
Yeah, I don't see that as that big a problem, though, Brad. I'm curious to know why you are. I mean, is that just because you feel like the whole world should be open source and you don't want to work on any tool chain that's closed source in any way?
No, it's just that now half of the sort of the value of the FPGA is that it is this dynamic reprogrammable thing, and yet anytime you want to hit that reprogrammability, now you have to do that off to, you know, sort of looping back, and you're writing VHDL or something on the other side of it. So it's like if you wanted to have your Forth plug into some apparatus that you have sitting alongside it, now that's outside of Forth again, and you're back to, you know, so you're sort of
I see what you're saying. You can't reconfigure the FPGA using Forth, is your point.
Yeah.
I see. Yeah. No, that's a very good point. And actually, I happen to work for a guy who is sort of a genius in this industry, and this is one of the things that he's really focused on making happen, is the ability to reconfigure a part of the FPGA without having to recompile the whole thing. But what I was going to say was that, for, you know, building a Forth for the RISC-V processor, or, you know, building a processor that is stack-based, which Forth would then fit on top of very well. I think those are really interesting research areas, and I want to see more on that.
Well, there are a couple on FPGAs. The EP32 is one of them, but not a single Forth. But if you can get 8 of them on an FPGA, suddenly that opens up some very interesting things in the market.
Get 8 of them on an FP. I'm not sure I understand what you're saying.
So one Forth machine on an FPGA is not that interesting commercially, but if you can have 8 of them cooperating, you can do some very interesting things, which the other chips I see just can't do it.
Oh, for like parallel processing.
Yeah, exactly.
There is, I don't know if you're familiar with James Bowman's work. There are some fourth implementations that are.
Well, so
on
James,
top
the
of a-
J1, then there's the H2. J1 doesn't have an interrupt. Maybe 800 LUTs or something. The P16 I think is 3,000 LUTs. Correct me if I'm, Dr. Ting, if I'm wrong. It just looks like the J1 looks sort of too stripped down to me.
But this is a really good point that parallel processing is becoming a huge part of industry. The robot that I work with every day uses an FPGA. And
there's some things I can do that are commercially very viable. Forgive me if I can't say more, but you know, I just can't do them on any of the chips out there.
Mm-hmm.
But I'm not an FPGA designer, so I'd be great if everybody jumped on the EP32 and we could have a whole bunch of these on a CPU, on a FPGA, and then there's some very interesting things that could be done.
Yeah, so having multiple fourth engines on one FPGA that are all running the same program, for example.
They're cooperating, let's say. They're doing different things, but yeah, they're cooperating.
Well, I like this idea that you can take, for example, an incoming picture, and you want to do some kind of convolution over it, and you can parse that picture.
So pictures are one example. Pictures are actually an excellent example. So what they do is they do a mathematical program on these, and so the whole image is subject to the same program. But that's ridiculous. You detect a line, you should be doing certain things on a line, and you detect a flat area, you should be doing different things on a flat area. So you know, 100 of these pictures would be just brilliant.
Mm-hmm.
The green array chip has nowhere near enough memory to do it, right? Because you need to keep a couple frames, and it's like, you know, each one is at least 24 bits, and you get 1,000 by 1,000 pixels. And I don't know, I did the math on that, but it comes out to some rather large number. Not that big, but you know, you need to be able to do this. There's lots of other examples.
So are there other people interested in that, or is that just the two of us?
You know, there's a guy who wants to do the Transputer thing, and there's a guy who did the, I don't know if you know the, give me just a second, the XMAS chips.
I don't know that one.
So very small company, they're doing well in audio now. So what they do is they have tiles, and each tile has a core, has one CPU, and 8 sets of registers. And so it can context switch, it has instantaneous context switching. And so you get one of these chips, and it has 4 tiles, meaning 4 CPUs. They used to have 8. So they actually took these 4 things, and they ganged up a whole bunch, and they did a hypercube with 64 of them. And actually, there's the core, Graph Core software in England, which is a related product. And so there's all bunch of, I mean, you look at the Calray in France, and then in they have I do what's needed, and I don't, you know, they're not software developers, right? So the whole, you want the software developers to decide what's in the chip, not the chip developers to say what the software guys do.
Yeah, no, that's that's so true. and you know, the opposite is also true. It's like, you can be a hardware developer and say, you know, for 2 extra flip-flops, I can give you this whole capability in your language. But the thing that you're telling me I have to do, I need, you know, a ton of real estate in order to happen. So it has to be a give and take, a back and forth.
Yeah.
Anyway, I guess it's just the two of us who are interested in that. I don't think anybody else is. So I'll shut up about it now.
Yeah, I don't know, this question though of sort of the perils of running on another platform and all of that, like that is a thing. Certainly I struggle with that question, and you know, it's on the one hand, you know, being able to get all the good things that you can do in interesting large platforms is cool, but it brings a barrel of complexity with it too. You know, we're all dialed into Zoom here on a highly complex layered platform, And wouldn't I love to be able to have that version of the stack that has less complexity, but that's a tall order too.
I think it's interesting that we may see in the future that our computers, like our laptops and things like that, become reconfigurable processors. That would be interesting, and it's possible because we're kind of almost going that way. We're starting to see things that look like they're trending in that general direction. And, so the things that James is talking about there are possibly a little stretch yet, but not that far off. I think that we're going to see something like that happening.
I think some of it is that in the near term, right, we've got vendors that don't have the right incentives, right? The FPGA vendors, they make their money by having the secret sauce inside of the FPGA, and you use your complicated tool chain that knows about the secret things inside the black box, and then maps across given a program. But what they're fundamentally trying to do is to not share with their competitors sort of the advantages of knowing the specifics of what's going on inside. And it's sort of, well, you can have the
Right.
CPU, but you don't get to see the instruction set.
Sure.
Well, and it's mostly, how do I fit something into the actual structure inside the FPGA when I don't know the actual structure inside the FPGA, right? So
Yeah.
one of the things my boss has been working on is trying to get okay, FPGA manufacturing. We're actually in high level talks with Intel right now. You have, this part of your FPGA is all the secret stuff, and that's closed source, and we won't mess with that. We'll use your tool to put stuff in there if we need to, but give us an area that you describe very clearly to us, and so that we can fit, a map into, and then let us just dork about with this one area, and not have to worry about. You don't have to worry about giving up anything there, because this one area is just pretty standard and it's not doing anything special, but we get to play with it now, right? So that's in very initial talks, but hopefully it's
were public domain FPGA tools around not too terribly long ago. I remember Bowman did a talk about some development that he did in end-to-end public domain environment.
There's some available for certain chips, which tend to be fairly low end, like for example, Lattice. I think there's a fully open source tool chain for one of the Spartan chips. Other people would know better than I would, but yeah, that is out there. But it has been as a result of reverse engineering, and there's all kinds of legal questions related to it. We're specifically not allowed to use it, unfortunately, to avoid potential future lawsuits. So the problem is that there's like open source, and the hobbyists will play with it and it doesn't matter. And then there's open source, and corporations can't use it for serious development because that may go away in the future.
Yeah, but once they have the protection breached, it no longer becomes viable as a product, because nobody wants to use it, because then somebody will come along and reverse engineer the product. I'm reminded of Trisend chip. Anybody remember Trisend? It was a processor core that had programmable logic around it so that you could implement peripherals. So you could have a one-chip computer that would do all of your interfaces that you would want. The problem with it was that once you programmed it and invested all your efforts into making your version of the Trisend chip and incorporated it in a product, there was no protection. Your intellectual property was there for the world to see, and it was very easy to come out with a competing product that had all that same intellectual property that they had stolen from your product. So the
Right.
Trisend chip, I feel I've been told that that's one of the reasons why nobody used the Trisend chip for actual products.
There's a processor sort of like that, the PSOC line from Cypress, but it has very little digital logic, a little bit of programmable analog, and then like an ARM Cortex M0 processor.
Well, I think that
but they're not very popular.
For a practical solution to that class of problem, I think pretty much anybody would just take some and plop it down with peripherals and do it all in programmable logic rather than have the processor core hard implemented. That combination of the thing in the Trisend era, that was a perfectly viable solution to the abstract problem. Now it's why would anybody bother doing that? Because you could have your core and your peripherals all in VHDL or whatever, and just plop it down on a entirely programmable chip.
Mm-hmm. Well, there are inefficiencies to macrocells, which having a hard-coded CPU avoids, and so you'll see a lot. Like for example, the robot that I work on has a hard-coded dual-core ARM7 processor on it, and then has a bunch of macrocells around that you can do whatever you want to with. And the only reason why they did that is because then the chip runs a little cooler and sucks down a little bit less power. It's not necessarily a huge difference, but sometimes in certain applications you're looking for every advantage you can get. And my understanding, I could be misinformed on this, but my understanding is that the whole reason why they did that, these are zinc chips from Xilinx. The whole reason why they did that was because people were complaining about the chip overheating, because they were implementing their IP core in it and then having problems with heat control. And they said, okay, well, we can't really solve the overheating problem, but what we'll do is we'll hard implement a very low power, very efficient ARM processor, and then people will use that for their computing, and they won't complain about the chip overheating anymore.
There's a frustrating analog to this in the GPU space, and one worry is that'll be where this will go. With GPUs, they similarly will have this sort of closed interior thing, and you get to sort of know something about the basic structure, and then oftentimes you'll have a runtime thing that you can pass a shader to in a particular format, and then it goes through whatever. But again, because the abstraction that's sitting on the inside is hidden from you, now the problem is that you're forced to, whenever you add new code, it's a big deal. It has to be provided as a whole unit and translated sort of by whatever driver. And so then the problem that you get is that yes, you can dynamically do things, but you can only do them if you can provide that big lump of stuff, and you're willing to sort of wait for the driver to chew over and process that. And
right. The end effect of it be that you can do enormously powerful things, but you can only do certain enormously powerful things, right? You try to do A, and because that's not one of the things that's been done, it's incredibly slow and it's crappy and you can't make it happen. But then you go to do B, which is perhaps computationally more expensive, and suddenly, whoosh, you're flying like the wind, because that's something that's been implemented at the high level. Yeah.
It's interesting that you're talking about that with graphics processors, because that's just what's happening right now with Nvidia and AMD. AMD's come up with a way of dealing with the enhancement of the image without using separate processors on the special hardware on the graphics processor, that actually not only makes it run faster, and allows it to do all of these various different things. And of course, they provide it as an open source, whereas with the Nvidia, you have to buy the new hardware all the time in order to keep up with it. And it's interesting that that this different way of handling it is actually faster than allowing the hardware to deal with it. And so Nvidia wastes silicon space where they don't need to. So it's kind of an interesting problem.
The other thing that's really interesting to me too is that there are I've been involved in robotics for more years than my body wants to admit. And back in the day when we were running on very constrained little 8-bit CPUs on CPM with image capture cards that could maybe do 256 by 256, right? We had to use all kinds of tricks to do image processing, like, you know, sending out using laser lines or using, you know, laser dots, or, you know, doing structured light in just really crude ways. And we had to do a lot of the processing too was like really, you know, just stupid tricks that didn't work all the time, but usually worked, kind of a thing, and were super low computationally expensive. And what's happened now is everybody just seems to throw all of those old tricks out the door, and then they just depend on some massively trained neural network to, you know, to do all the work at a very high level. And I keep advocating for like a combination of those two things, you know, like use the old tricks, and then when they don't work, then shell out to the other thing. And the reason why I think that's kind of related is because it's this thing of you can't innovate. You have to either do one huge neural network and do everything in this fancy new modern way, you know, in this very narrow definition of it, right? And then when you try to go back and do something cheap and easy from the old days, everybody's like, what? You can't do that, you know, and it can't even be implemented because of these problems with closed source and other stuff. So I've run into that a lot. I can do demos on, you know, a little 32-bit ESP chip with a camera and go, look, do this. This is running on a 32-bit chip in you know, without any FPGA acceleration. Look, it works, you know, 90% of the time. And then they try to implement that solution in a modern, you know, GPU, you know, God knows how many bits wide, parallel processing and all the rest of that, and they can't do it. It's not, you know, the implementation is not possible without a massive cost because it doesn't fit within these narrow constraints. Okay, so when did this become the FPGA computer vision meeting as opposed to the... Has anybody done computer vision stuff with Forth? Let's get it back on topic.
Yeah. It's out of my realm. I've done a little bit of signal processing, but not video processing, which is a little bit different.
There was a very early application of Polyforth where they were processing wood slats for pencils. And then later on, that evolved into a production line printed circuit board inspection system. But that's the nature of the antique applications of Forth to image processing.
It's funny though, because Forth is an extremely efficient language, and a lot of the operations required for machine vision are not super complicated. You know, the convolutions are not necessarily tremendously complex computations, or you know, but you're doing a lot of them over and over and over again. It seems like it would be a good application for Forth. I'm surprised more people haven't played around with that.
I suspect it's a timing thing, you know, just at the moment when we've now got enough cycles to do these things efficiently, we've sort of, Forth has moved outside of the zeitgeist, and so we're not, you know, it's not, now we're driving these things in Python with an interpreter that's god awful slow, but it's fine. So performance
More
is
hardware. Yeah.
Yeah,
We are the redheaded stepchild, aren't we?
indeed.
There are a lot of libraries for this sort of thing available in other languages.
Well, yeah, it's interesting to me too that a lot of the machine learning stuff, everybody thinks it's being done in Python, but then when you look a little bit deeper, it turns out that, you know, maybe they prototyped it in Python and it was a nightmare, and then they went and re-implemented it in C, and then they re-implemented part of that in assembly for 5 different platforms in order to get performance under Python, quote, under Python, end quote, that was reasonable. So
yeah, you're
I mean,
really just stringing together a bunch of these very you know, very tightly optimized kernels, and Python's just there to orchestrate it. So
right, yeah, exactly. And you know, Python's not a horrible. Well, okay, maybe it is a horrible language, but
it's not the
it's
worst
one
language for that kind of thing. I mean, unfortunately, that's, you know, and it's I think, you know, it won in that domain because it was just approachable enough for sort of a range of folks. And
well, you know, I think the really big thing, and this is another example of something that I haven't really seen in Forth. So you have the REPL, right? There's lots of Forth REPLs. That's great, but Jupyter notebooks are.
you need to check out Cozy.
Say it again.
You need to go check out Cozy.
Definitely, I consider that my competition.
Yeah, but Cozy isn't Forth, so I mean, anyway.
Cozy is Forth. Cozy is open Forth.
Okay. I'm sure it's buried in there somewhere.
It's not buried in there. It is constructed in open Forth. It is a vocabulary in Forth.
Yes, okay. So I can go back and use open Forth and just ignore and hope I don't crash into any of the words that were defined in Cozy.
Well, that's easy.
Okay. Anyway, but the point is that those Jupyter notebooks make it really easy to take a step down and then back up and then take a step back down again and then back up and keep trying. Like, you know, maybe I need an extra layer here, or maybe I need to have this many inputs to this layer as opposed to that many inputs to this layer. So you can go back and forth and fine tune the neural network without having to redo all of your work, and it presents it in a graphical environment. And that, I think that makes it very, very valuable. So just out of curiosity, Bob, have you done anything with machine learning?
Actually, I learned APL in the first place because I was in visual psychophysics, and I could express operations on a pattern across the optic nerves. Across, you know, 250. Now you can do that. You can implement that. But that's why I learned APL in the first place, to learn the arbitrary dimensional math to go and express these sorts of algorithms. And actually, right, I'd say the memory was probably the area that I was most interested in. But the difference with Jupyter is, one, it's had a quarter century of development, and two, it's got graphics interfaces, and is, I mean, Cozy at this point in time is just a single person's creation. So, but there's a good video by the guy who's involved in Anaconda when he discovers Forth. It's linked on my videos. But he gave a talk to a whole Python or Anaconda group on discovering Forth. And wow, it sort of is like, it was, you know, just, it's definitely interesting. And he was giving this talk to the K group, KX group. So that's.
All right, I'd like to I'd like to wrap up the formal meeting. So we'll the start of the recording is ceremonious, but let's have the unceremonious stop of the recording, Brad.